So the skater starts off high, then goes low. Starts off slow, then speeds up. So we see this oscillating motion in our skater. Let's bring out a bar graph and look at our different types of energy and a speed monitor. So notice the greatest speed is exactly when the skater hits the bottom of the ramp. Now let's look at when kinetic energy is maximum. Right now. Wait, now. There you go. As our skater's at the bottom of our ramp, our kinetic energy is maximum. Where's our potential energy maximum? Right here, at the top of the ramp. Notice there's no speed at this point and no kinetic energy. Let's watch that total bar. You see the total remains at the same number? That number matches the max KE or the max PE. It matches the addition of either two at any random point. The total energy is referring to the total mechanical energy in the system and is conserved throughout the entire motion. Let's explore some starting heights. So if we take our skater and we start them at position 5, you're wondering if they'll return to 5 on the other side. And you're like, well, they do, because energy, total energy doesn't change. It all turns back into potential energy on the other side. If we were to add in some friction, start our skater at 5 on one side, we would see that they do not make it to 5 on the other side, and they make it even less high. Now what's happening? You see that total bar is still remaining the same, but some of our energy that was mechanical being converted back and forth is now just sucked into the thermal energy section. That's where the friction goes. That's the energy that friction makes, But there's another way to make our skater not reach the same height even if we're frictionless. Let's create that same type of ramp but cut the end off like this. Let's go to no friction. So we'll start our skater at 5 and we'll expect them to re-reach that same 5 position. But they don't. Let's check out what's happening here. Start our skater at 5. They release on the other side and notice at maximum height, they're not reaching that 5 because some of their energy is stuck in the form of kinetic, having horizontal velocity. Let's take what we learned here and let's apply it to some more advanced roller coasters. All right, in our packet, we have a roller coaster and it's going to go through some different locations. You'll see location A, B, C, D, and E. You should be able to predict which one of those locations has the most potential energy, which one of those locations has the most kinetic energy, and which one of those locations has the most total energy. So A has the most potential energy. This is true. It is the highest one, and potential energy depends on height. Here we have enough information. We have the M, let's make G 10, and we have the height, 30. MGH. So we get our energy in our system is 15,000 joules. Our kinetic energy is 0. So when we plug 0 into 1/2 mv squared, we get 0. This allows us to find our total energy, 15,000. Now, what you learned in that simulation is that total energy, this number, cannot be changed as long as there's no friction. That energy is just going to slosh back and forth between potential and kinetic. All right, now in each location, the height is listed. So for B, I can go in and find the height. I can take M, I can take G, I can take H, new H, it's 15. This comes out to be 7,500 joules. But at B, we don't know the speed, so I can't just do what I did before where I did 1/2 m and plugged in the speed squared to find KE. We need to think about another technique to find the kinetic energy. So perhaps we can take the total energy here and subtract off what is in the form of potential. What's left over must be in the form of kinetic. So here we find another 7,500 joules in the form of kinetic energy. This actually allows us to go in and solve backwards for the speed that we must need here. So we get 17 meters per second for our speed here. All right, let's try the same process again down at the bottom. Down at the bottom at location C, you have a height of 0, potential energy 0. So you're like, what type of energy do I have then? It all has to be in the form of kinetic. You can take that kinetic energy and set it equal to 1/2 m v squared. And we get a speed of about 25 meters per second. Let's repeat that for locations D and E, and then we'll compare answers. Pause and try it out. All right, and here we get a speed of 20. Good. You can try out energy conservation on some different problems and see how you do.